All right, so let's talk about another model, which is the model that we model of an atom that we accept as being the accurate model today. Oh, wait a minute. The quantum mechanical model, that does not look like mechanical at all. Quantum mechanical model of an atom. And so we've considered light as a wave. And we talked about amplitude and crest and wavelength and frequency, all of those things as light behaves like a wave. And so that experiment that I said you could do for extra credit, experiment 4.1, that's basically an experiment to prove that light behaves like a wave. And so the way this experiment works is basically if you have an obstacle, did you do something? If you have an obstacle, like a piece of paper, cut some slits in it, and then you shine a light through it, what you're going to notice is that there'll be a pattern of light, bright light, white pattern, and then a dark pattern in between those where the white spots are. On page 99, you'll see a diagram of the experiment that a guy by the name of Thomas Young did in the early 1800s. And he discovered these light and dark patterns. And so the reason those are there is because of light behaving like a wave. And what you're seeing with the light and dark patterns is you're seeing constructive interference. All right? And constructive interference is basically where the light waves reinforce one another. It actually doubles the amplitude. All right, so what would happen when you had this constructive interference is that you would have two light waves like this here, and because they're exactly the same light waves, they would actually combine together to produce another light wave that's twice the amplitude of the two previous ones. All right? And do you remember what we said amplitude is connected with? Wavelength is connected with the color of the light. What's amplitude associated with? Brightness. The brightness, right? So the greater the amplitude, the brighter the light. And so that's why you see these bright patterns that it shows in the drawing there. By the way, instead of worrying about, I'm going to get the whole class +1 today. I did that in a while. You guys participated well in the experiment. So +1 for everybody. Congratulations. So that would double it. That's constructive interference, but then you also have what we refer to as destructive or destructive interference. Totally misspelled that. No, that's right. Here. All right, destructive interference, and that's when light waves are the opposite of one another and thus cancel each other. Cancel each other out. All right, so in that case there, you've got a light, you have one light wave that's like that, you'd have another light wave that's like that, and they cancel each other out. So that's why you have the dark patterns. And so this only happens because light behaves like a wave. So this was an experiment that proved light behaves like a wave, but then there were other experiments And we mentioned this last week that light actually behaved more like a particle rather than a wave in those experiments. And so light will do that as well, and we call that a photon. So a photon is a light particle. It's light behaving like a particle instead of a wave, and we refer to that as a photon. And Albert Einstein proposed this explanation of light's behavior in the early 1900s. He said, okay, you guys have done the work saying it acts like a wave, but sometimes it acts like a particle. So if we think of it as a particle, then that explains some of the other behavior that we have with light. And so then, based on that, there was an Austrian physicist named Erwin Schrödinger. And Schrödinger said, well, if light behaves sometimes like a wave and sometimes like a particle, maybe electrons behave like that as well. And we've actually seen the same pattern. If you shoot a beam of electrons, we've seen the same type of interference pattern that we've seen with light waves. So electrons behave the same way. When it was this idea of electrons behaving like a wave and also behaving like a particle that led Schrödinger to come up with this quantum mechanical model of an atom. All right, so let me give you a definition of the quantum mechanical model. The quantum mechanical model describes an atom this way. It says, quantum mechanical model says, make sure you know this definition, says, it says that the electrons can only absorb specific amounts of energy. That's nothing new. That's like in the Bohr model. Like the Bohr model said. Remember, the Bohr model said that electrons travel on these concentric circles, right? These orbits around the nucleus, and as the electron would jump from one circle to the next, it would emit light, right? And so this was similar to the Bohr model, but here's where it differed. It said the same as the Bohr model, but also that electrons are not confined to specific orbits. Instead, they are confined to specific orbitals. An orbit was too simple. They were confined to orbitals. So what are orbitals? We need to define that as well. Orbitals are 3D shapes around the nucleus in which an electron is constrained. So I think I said this last week, right? A circle is a two-dimensional shape. We don't live in a two-dimensional world, right? We live in a three-dimensional world. And so these electrons are existing in a three-dimensional world. And so they're not simply on this circular two-dimensional path. Instead, the circle that Bohr talked about is really a sphere, right? It's like a three-dimensional circle. we would call that a sphere. And so the electron can actually be anywhere inside that sphere. It just can't go outside of it if it stays inside that orbital. So kind of think about that like a dog on a chain, right? You put a dog on a chain, he can go anywhere inside the perimeter of that chain. He can jump up as long as the chain will let him go that high. He can dig down into the ground and go below it. He can go anywhere around where that point is that he's locked in. That point's the nucleus, right? And so the electron can be anywhere in that orbital around the nucleus. So what was a circle in Bohr's model turns out to be a sphere in the quantum mechanical model. And as we've discovered now, there's more than just the spherical orbitals, and we're going to talk about those in just a moment. But orbital is another name for an orbital. This is also called, aka, an electron cloud. So you may hear it referred to electron cloud. Or I guess really, since we're talking about orbitals, also, I guess I should say electron clouds. Another name used for orbitals. All right, so any questions about that? Does that make sense? And we can see like an example of the spherical orbitals on page 101 in your book. There's some nice 3D drawings there of what we refer to as the s orbitals. So we've got s orbitals there. Should be easy to remember. S for sphere, right? Spherical. Should help us to remember those. Turns out there are other orbitals, though. There are other shapes. When we speak of orbitals, we're generally talking about the shape of that orbital. So if we say an s orbital, it's a spherical shape. There's also a p orbital. Sorry, there's a p orbital, which is a dumbbell shape, so you know, the old in a cartoon, they always look kind of like that, but it's really more of like a shape like this. Sort of looks like infinity, right? The infinity symbol. So p orbitals are dumbbell shaped, and then d orbital is the last one we're going to focus on in this class, and that one's too complex for me to draw. They have a representation of it here. If you look on the look on page 102, you'll see the p orbitals, and then the d orbitals are on page 103. There's actually f and g orbitals as well, but that's beyond the scope of this course, so we're not going to deal with that. We're just going to focus on the s, the p, and the d orbitals. And so those are, just think of those as, you know, shapes of orbits around the nucleus that an electron may be in, depending on which orbital it is. As you see with the in the book there, the p orbital actually there's actually a total of 3 orbitals in this p shape. So in the p orbitals, there's a total of 3 orbitals in it. So you've got like one that runs along the x-axis, one that runs along the y-axis, and you've got another one on the z-axis. So you've got another dumbbell shape that comes out like that. And they do a much better job of representing that on page 102 in the book. But the point is, with s orbitals, there's 1 spherical orbital. With the p orbitals, there are 3 dumbbell-shaped orbitals. And then with the d orbitals, there's a total of 5 orbitals that have those more complex shapes. And so I want to write that down for you. This is really the key information that I want you to know about these various orbitals. Okay, it's that s orbitals. So for them, s orbitals are spherical in shape. There's 1 orbital per energy level. And we're going to abbreviate energy level as EL. And when I say energy level, remember when we said that Bohr's model was extremely accurate for the hydrogen atom, right? And we said, so with Bohr's model, you had the proton nucleus, right? And then around that, you had these concentric circles. And we said that the electron wanted to stay here in the orbit that was closest, but when the energy was added, it would jump between these energy levels. And so remember, we said this was like energy level equals 1, its energy level equals 2, n equals 3. So that's what we're talking about when we say there's one orbital per energy level for the s orbitals. So there's a energy level 1 s orbital, there's an energy level 2 s orbital, and so on. And the other thing to note about the s orbitals is that they start at energy level 1. And we'll see what that means. Some of this stuff's not going to make a lot of sense until we talk about it a little bit more. We move on to the p orbitals. The p orbitals are dumbbell shaped. They have 3 orbitals per energy level, and they start at energy level 2. And then finally the other orbital we're going to cover in this class are the d orbitals. D orbitals they have a complex shape. They have 5 orbitals, and they start at energy level 3. And so you need to know this. This is the least energy required is down here. Electron requires the least amount of energy to be in the s orbital, and as you go across this way, this is the highest energy required over here. All right, so make sure you know that, you understand that about these orbitals. So, like I said, Schrodinger based this model on the assumption that electrons, like light, behave both as waves in some circumstances and as particles in others. And we call this the wave-particle duality. And that's the concept that light as well as many subatomic particles have properties of both particles and waves. In some experiments, it behaves like a wave, like the experiment that you can do at home, like the experiment we've done with light and with electrons, where you see those bands, and then other times it behaves like a particle. So we call that the wave-particle duality. I'm not sure if I want to open it up for questions yet, because I think this is still going to be sort of fuzzy until we talk about it a little bit more. But I guess any questions that you have that it's like, I can't go on until I know the answer to this, Mr. Walker. Something besides why dads shake their snacks in their hand. We got that established last week, right? We got it down. One of life's monumental questions now answered. You're welcome. Yes? Schrodinger. So his name is, I'm not going to ask you that on the test, but it's just to tell you the correct spelling is C-H-R-O with the 2 dots over the O. I can't remember what that's called. Schrodinger is credited with the quantum mechanical model. He was an Austrian physicist. All right, so our understanding that electrons can travel within different orbitals requires us to also understand which orbitals they typically exist in for a given atom. So we're going to be able to, we talked last week about the ground state. Electrons want to be in the lowest energy level that they can be in. They want to require the least amount of energy possible as they're orbiting around the nucleus. And so the energy level that they're typically in, where they typically exist, that's what we refer to as the ground state, all right, of a particular atom. And so there's two things that we need to consider when we talk about where the electrons are typically in an atom. And those two things are, we need to remember that each orbital can only hold 2 electrons. Each orbital can only hold 2 electrons. And so if the s orbital only has 1 orbital per energy level, then what's the max number of electrons that for a given energy level the s orbital can hold? It's just 2, right? So max of 2 electrons for a given energy level, right? The p orbital, however, has 3 orbitals per energy level. So what's the max electrons it can have? 6, right? 3 orbitals, max of 2 apiece, so max of 6 electrons. And then finally, since there's 5 orbitals for the d orbitals, then this can have a max of 10. All right, so that's one thing that we need to know. And so, S has 2, P has 6, and D has 10. The next thing that we need to remember is that electrons fill orbitals starting with the lowest energy ones and then filling higher energy orbitals. And we refer to this as AU, F, B, A, U. That's the Aufbau principle, which says that electrons fill orbitals starting with the lowest energy ones, then it fills the higher energy ones. Okay, so the first place you're going to find an electron is going to be in the s orbital at energy level 1, because the s orbital starts at energy level 1. Requires more energy to be in the p orbital. And notice that the p orbitals, they don't start until energy level 2. So what's going to happen is as an electron, as an atom, as the electrons fill the orbits around an atom, you're first going to have the energy level, the s orbital at energy level 1 filled, and then you're going to have the s orbital at energy level 2 filled, and from then it's going to fill the p orbital at energy level 2. Since the d orbitals don't start until energy level 3, then it's going to jump back down and start filling the s orbital at the 3rd energy level. And from then it's going to fill the p orbital at the 3rd energy level. And we're going to see that it does something kind of weird next. You would expect it to go to the d orbital, but actually it takes, at the 3rd energy level, because they start there, but it actually takes less energy for it to fill the s orbital at the 4th energy level. So it'll do that first, then it'll go to the d orbital at the 3rd energy level, and then it'll jump to the 4p energy level orbital. And we're going to walk through that in a second. I'm going to show you, that's the whole reason I've got the periodic table here, because I'm going to show you how the periodic table is going to help you remember that order, okay, in the way that those electrons fill. So fill those energy levels. But let's do an example real quick on page 105. And the example on page 105 says, where are all the electrons of a carbon atom that is in its ground state? carbon atom looks like this on the periodic table, right? And it's got 6 as its atomic number. So how many electrons does a carbon atom have?
6.
It has 6, right? The number here technically represents the number of protons, but there's always the same number of electrons as there are protons, right? Because overall the atom is electrically neutral. They balance out the positive and negative charges. So it's got 6 electrons. So we got to figure out where do those 6 electrons live when it's in its ground state. Okay. And so, like I said, first of all, according to this principle here, it's going to fill the orbitals that start with the lowest energy ones. So the lowest energy level is going to be the s orbital that's at energy level 1. Okay? What's the max number of electrons that energy level can hold? 2. S orbitals can only hold 2, right? Now we can't move from there to the p orbitals because remember, the p orbital starts at energy level 2. So next, did you have a question? Okay, I thought I saw a hand up. So next it's going to go to the 2s orbital. That is the s orbital that's at energy level 2. And again, the max number of electrons that an s orbital can hold is 2. And so we've got a total of 6 electrons that we've got to account for. So it's going to fill that one up as well. Okay? From there, because it takes more energy to go to the 3s level than it does to go to the 2p orbital, then it's going to go to 2p next, because that's when the p orbitals start. They start at energy level 2. So for the 2p orbital, that is the p orbital at energy level 2, it can hold a max of how many electrons? Huh? Did I hear 6? Yes, 6. That's right. Max of 6 electrons for a p orbital. But how many electrons do we have left? We've already accounted for 4. We only have 2 left, right? Because we have a total of 6. So in the 2p energy level orbital, in the 2p orbital, that is the p orbital at energy level 2, we only have 2 electrons in there. So this is where all of the electrons exist in its ground state for a carbon atom, right? And so what we refer to this as, this is called the electron configuration. And that's the shorthand way that we would write that out. If you look at the answer that they gave in the book, they said, well, there's 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 2 electrons in the 2p orbital. But this is how we would write that out. That would be our shorthand notation for that. Okay, so just to make sure that you understand, when I write 2p2, this 2 here refers to the energy level. This right here refers to the orbital type or shape, right? And this refers to the number of electrons in that orbital. So for the 2p orbital, what's the highest this number could be? 6. The p orbitals have a max of 6 electrons. Because there's technically a total of 3 orbitals that are in there, right? 3-dimensional shapes, 3-dimensional paths that electron could be in. All right. Questions about that? All right, I'm going to show you how to find that, right? Using the periodic table, I'm going to show you how to determine that, the electron configuration using the periodic table. And we'll go to page we'll go to page 107, and let's look at example 4.2, and we'll do that as an example problem. So I'm going to slide this down so that we can see everything. All right, let me make sure I can see that in there. Yep. Oh, this is a little bit off. So let's move that over that way. There we go. Okay, cool. So we're going to use the periodic table. That's the easiest way to write down these electron configurations, okay? And so they ask us to find the electron configuration for silicon. Silicon's right here, 14. All right? So 14 electrons that we've got to account for, right? So the way that we figure out what the electron configuration is you're basically going to count, you're going to go through the periodic table. You're just going to count through that until you get up to this 14. All right. The only thing that you have to remember is you need to think of helium as being over here in column number 2. All right. So in your mind, slide helium over to right here. And the reason why we're doing that is because columns are going to represent the s orbital. What's the max number of electrons you can have in the s orbital? 2. And so how many columns are there? 2. All right. What's the max number of electrons you can have in the p orbital? Huh? 6, right? Guess how many columns there are right here? 1, 2, 3, 4, 5, 6. Don't think of helium here. Think of helium as being over here, okay? There's 6 columns here. Those 6 columns correspond to the fact that there are a maximum of 6 electrons in the p orbital, okay? So this is the s orbitals. These are the p orbitals. And in the center here, you have the d orbitals because there are 10 columns in the center here, okay? And so here's how we're going to do the electron configuration, all right? For silicon, Si, we're going to say, first of all, the first orbital is the 1s orbital. If we forget which one it is, the 1, the energy level corresponds to the rho on the periodic table, all right? And like I said, these 2 columns correspond to the s. So as we count over from left to right and down the chart, we first encounter the 1s orbital, and it's full. Next, there's nothing over here on the first row, right? So we jump down to the second row, which corresponds to energy level 2. And the first thing that we hit is we count from left to right as we encounter the 2s orbital. We count over 1, 2. There's 2 electrons there. That one's full. Now, as we move over from left to right, we encounter the p orbitals. We're on energy level 2, so it's 2p, right? And we hadn't gotten to silicon yet as we count over 1, 2, 3, 4, 5, 6. So all 6 of the electrons are in that p orbital. It's full. All right? As we continue to count over left to right and down, next we encounter the 3s orbitals. 3s. We start counting over from left to right. 1, 2. We don't hit silicon yet, so we write a 2 down there because we're out of the s orbitals now. And then as we move over from here, we hit the 3p orbitals. So we write down 3p. And as I count over, starting here, I go 1, 2, and I hit silicon. And so we have 2 electrons in the 3p orbital. And we're done. We made it all the way to silicon. Does that make sense? We're going to do another one, but does that kind of make sense? You kind of get that? See how the periodic table will help us with that? Questions? There's 2 gotchas. One is that you have to think of helium as being over here in order for this to work. And then we're going to talk about the next gotcha. But any questions on how I got that? So if I ask, yes?
How do you count over? That's why I'm kind of confused.
So you don't really have to count over if you just realize that they're full and you know how many electrons there are supposed to be in each one. But the reason I'm counting is because if you think about helium here, we're just counting over from left to right until we get down to where silicon is. And if we haven't hit silicon yet, we know we need to keep going. So we know this is the 1s orbital here. And so I'm counting over in 1, 2. If I counted all the way to silicon, I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so my point is that my finger had to touch all of those in between. And so I have to recognize that there's an electron that corresponds to each of those points that I counted on there, right? So with the 1s one, it holds a max of 2, so I went 1, 2, and so I know it's full. So that's why I put 2 electrons there. Then I jump down to this one, 1, 2. It's full as well. When I get over here to the 2p, does this at the most inconvenient times. When I get over here to the 2p ones, and I start counting, I have it. Come on. There you are. Okay. It'll be here in just a second. I'll edit this out of the video so we won't have to wait these uncomfortable 20 seconds. There we go. Okay, so 2p, and I start counting to see if I get to silicon. 1, 2, 3, 4, 5, 6. Well, I got all the way to the end of the p one, and I didn't get to silicon yet, so I write a 6 for 2p. 3s, 1, 2, still haven't got to silicon, so I write a 2 for 3s. Now I'm on 3p, 1, 2, I hit silicon, so I have to stop right there. So 2 is what I write down for 3p. That's why I wrote this 2 down right here. Right? If I had been counting the phosphorus, I'd have gone 1, 2, 3, and instead of a 2, this would have been a 3 right here.
And if silicon was a row down, it would be 4p.
That's right.
Okay.
Exactly. Yep. So the rows correspond to the energy levels. Right? The section on the periodic table tells us what orbital it is, and then however many numbers it is over from the left tells us how many electrons we have in that area. So if I were to give you, here's something else that's kind of cool. If I were to just give you this electron configuration and ask you what element it was, you should be able to add up all of these numbers at the top, right? Because that represents the number of electrons in it. And if I add all those up, I come up with 14, which matches the atomic number on the table. So you'd be able to tell me that this was the electron configuration for silicon. Make sense? All right, let's do another one. Let's do palladium. All right, so palladium is down here, 46. All right. So here's the cool thing. Palladium's down here. Palladium is after silicon on the periodic table. So actually, I could just copy everything down up to this last one because I know it's going to fill all of those orbitals, right? I know as we count through the periodic table that that's all going to be full. All right, but now when I get to the 3p one, which started here, 1, 2, 3, 4, 5, 6, I still haven't made it to palladium, so I can write down 6 for 3p. So I made it all the way to there, right? So I jump down to row number 4. This is 4s. 4s is full, so 4s2. Here's the other gotcha. I told you there were 2 gotchas when you use the periodic table, right? But as I count over from here, this time I don't jump all the way across and go to p. This time I hit my d orbitals first, right? So we're on row 4. We're on the d orbitals. But where, according to my notes down here, where do the d orbitals start? They start at energy level 3. So that's the other gotcha. When you hit the d orbitals, you have to take the energy level, whatever row you're on, and you have to subtract 1. All right, so when you hit the d orbitals, this isn't actually energy level 4, it's actually energy level 3. And the reason why we have to do that is that even though the 4s orbital is on a higher energy level, it actually requires less energy to fill the 4s orbital than it does to fill the 3d orbital. So electrons will go there first, and then they'll go next to the 3d orbital. So you just have to remember when you hit the d ones, subtract 1 from the row number. Okay? So we're going to count over, see if we get to palladium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We didn't hit palladium yet, so this 3d orbital is full. Next, we hit the 4p orbital. 1, 2, 3, 4, 5, 6. It's full as well. So we jump down to row number 5. Over here, rubidium. 5s is also full. 5s2. And then we hit the 4d orbital. Remember, you subtract 1 from the row number to get the correct energy level. And we count over 1, 2, 3, 4, 5, 6, 7, 8. When we get to 8, we hit palladium. And so that's how many electrons are in that orbital, and we're done. Does Does that make sense? Yeah? Can you guys remember the two gotchas? Right? What are the two gotchas? When using periodic table for electron configurations. Number one, think of He as directly to right of H, right? And subtract 1 from P, no, not P, D orbital energy level. So even though the first one you encounter is on row 4, you need to make sure that the first energy level you write down for D is 3. All right, so the last thing that I want to go over very quickly is, if there are no questions about that. Anybody confused at all? Yeah, I mean, you don't, the reality is you don't really look at it and go, 1, 2, 3, 4, 5, 6, right? You don't really do that. What you do is you go, palladium's way down here, and so I know that everything up to that point is going to be full. And as long as I remember that S can hold a max of 2, P holds a max of 6, and D holds a max of 10, then I do use my periodic table to count it. And I go, okay, it's 1S, right? 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P. I'm writing all this stuff down, 5S, and I'm writing that down.
The dad grunt.
Yeah, really. I'm writing that down as I'm looking through there. I know this one's full. I know this whole row is full, so there's an S and there's a P here. I know this whole row is full. There's an S and there's a P here. And then I know this whole row is full, so there's an S. There's a D, which I had to, take the energy level down, and there's a P that's full on that one. I get to row 5. There's an S that's full. And so these here, I just know they're all full. And I just know that S has 2, S has 2, P has 6, S has 2, P has 6, 2, this one has 10, this one has 6, this one has 2, and then when I get to the 4D, that's when I actually count over and I see that it's 8, right? And that's when I do 4D 8. So, I don't expect you guys when you're doing the test to be going like that there, until you kind of get to the end there and you're like, okay, it's 8 over from the left, and so I write 8 down there. The last thing that I want to show you is these are kind of a pain to write out because they can get really long, right? So there's an abbreviated electron configuration, all right? So the abbreviated, is it 2Bs? Yes, abbreviated electron configuration. It's lists the last element on the previous row, then lists the rest. All right, what does that mean? Well, so for example, for palladium, palladium's here. The last element on the previous row is krypton right here. And so if I wanted to do the abbreviated one for palladium, I would do krypton. I would write the symbol for krypton in square brackets. And then I would start counting from there. So here, I'm in the 5s orbital. 5s, it's full. 5s2. And then from there, I hit the 4d orbital. 4d. And I count over just like we did before. I count over 8. 1, 2, 3, 4, 5, 6, 7, 8. And I hit palladium. So that would be the abbreviated electron configuration for palladium.
But that's not some.
So what? What is it?
That's the same with krypton.
Well, it's the abbreviated electron configuration for palladium. And so what you write first is you write the last element in the previous row first. And the reason we do that is because look at this right here. If I were to write out the electron configuration for krypton, it would be that. Right? That's the electron configuration for krypton. So we basically say that it's the electron configuration for krypton plus these additional ones. Make sense? And so there's an example in the book that we could do on page, they ask us to do it for 10. So let's do it real quick for 10 and we'll call it a day. So if we look at 10, the dad grunt. That's so funny. Dads, only dads do that? Yes. Yeah. All right, TN. So only dads do the shaking of the. But see, that's just wisdom.
No, I saw my friend at lunch. He was doing the same
See?
thing.
It's like I'm getting it
And
right
I
in the
was
middle.
like-
I'm getting it in the middle so that I don't throw it past my mouth, you know? It's from years of experience of smearing stuff all over my face because it wasn't in the middle of my hand, you know? Especially like M&Ms that have started melting or something like that. You know, they're going to leave a mark. All right, 10. Where is 10? 10 is SN number 50. So right here. Right? So it's just like we did on the last one. Let's don't do 10 because we've already done one here. So let's do instead, let's do right above it. Let's do germanium. All right, GE. Let's do the abbreviated electron configuration for germanium. And so we start with, since it's the abbreviated one, we start in brackets with whatever the last element is on the row before germanium appears on. What is it? Argon, right? That's also, if you want to look in your book, it doesn't show it on this one, but it's in column 8A in your book. So if you look at the front of your book, you'll see that there are labels at the top of each column. So we're basically going back and getting the last element that was in column 8A as you counted through the periodic table. So argon, and then we start from here. So we say the 4s one is full, 4s2. From there, we hit the d orbitals, and you have to lower the energy level to 3. 3d, it's full, so we write a 10 there. Make sure you know that's a 10 and not a 6. And then, so that gets us all the way to there. And then when we start counting here, we're going to be in the 4p orbital. And we count over 1, 2, and we get to germanium. So that's it. Does that work? Make sense? Any questions about any of it? Yes?
Should that be 2s squared or is it 4s squared?
Let's see. Well, we started with argon.
It's 4.
We started right here, and then we counted over we go down from argon to this row. So 4s is next. 4s2. Does that make sense? Any other questions? It is kind of wacky when you first do it, but it's actually a very simple concept once you get it down. So, big hint. The electron configuration is what your quiz next week is about, all right? So make sure you understand how that works, both the full ground state electron configuration and the abbreviated electron configuration, all right?
So when we're doing our homework, should we use the abbreviated one?
It'll tell you one or the other. Yep. All right. Have a good week, guys.